Hello students, myself Pawan Kumar. So I'll be taking inorganic chemistry for paper 6.2. So in first we shall see about organometallic chemistry, that is first chapter. So first of all we shall know what are organometallic compounds. So organometallic compounds are those compounds which contain at least one carbon metal bond. That means it should contain one carbon and one metal. So where metal can be any of these metals: magnesium, lithium, lead, zinc, sodium, etc. Organometallic compounds are named by simply adding the name of metal to that of organic group bonded to the metal. So some of examples here we can see CH3 MgI, methyl magnesium iodide, CH3 CH2 MgBr, ethyl magnesium bromide, CH3 Li methyl lithium, CH3 CH2 Pb, that is tetraethyl lead. So other way you can define these organometallic compounds. An organometallic compound is broadly defined as one that involves one or more carbon atom of an organic group or molecule and a transition metal, lanthanide, actinide or main group metal atom. So this is one way of defining an organometallic compound. That means uh, carbon atoms of organic group or molecule, or it can be an any transition metal. The other way, second way of the definition is compounds in which metal atom, that is including non-metal and metalloid, that is which are less electronegative than carbon, that is metal attached to the carbon atom should be a less electronegative compared to the carbon, is bonded directly to a carbon atom of at least one organic group, radical or molecule, are also known as organometallic compounds. Third way, organometallic compounds are those in which central metal atoms are bonded directly to the carbon atoms of hydrocarbon radicals or molecules. Term metal generally stands for elements less electronegative than carbon. So these are some of other ways you can define an organometallic compound. So one thing you should notice here is, so here carbon atom is not only a carbon, it is an organic group or molecule. So next, coming to the nomenclature of organometallic compounds. So to know the nomenclature of organometallic compounds, you should be aware of how we have named the coordination compounds. So some of the rules which apply to the coordination compounds are also involved in naming of these organometallic compounds. Along with the rules which are used for naming of organometallic compounds, some extra additional rules are also followed in naming of organometallic compounds. So some of here additional rules which are given. The first point is ligands without prefixes mono, di, tri, etc. are named in alphabetical order irrespective of charge on them. The presence of hydrocarbon ligands in the coordination sphere is customarily indicated by names of their radicals such as methyl, ethyl, phenyl, although they are known to behave as anions in several cases. So thus according to this rule we can see, so below the first example, potassium, within the coordination sphere there is boron along with an phenyl group is named as potassium tetraphenyl borate 3 complex. So another one, so you can see potassium and within the coordination sphere, that is SbCl5C6H5, is named as potassium pentachloro phenyl antimonate 5 complex. So this is how you have to name an organometallic complex. So you can see organometallic compounds are generally nothing but you can see it is somewhat in linked with some coordination compounds. So if you are aware of coordination compounds, and then you can easily understand the organometallic compounds. In case of unsaturated molecules or groups, that is those containing more than one uh, generally conjugated double bond, ligand is named with the prefix eta, where eta n is number of carbon atoms in the organic ligand, attached to the metal. So here you have to be aware of this symbol eta. So eta is generally, when you come in the next topic we will see what is eta. Eta denotes the hapticity of the ligands also. If it is 1, then we call it as monohepta. If it is 2 eta 2, then it is dihepta, so on. You have to 7 8, the number of, you can give up to the 7 and 8 number. So where you can tetrahepta, pentahepta, hexahepta, hepta, heptoligands. When some ligand atoms involved in double bond, or some ligand atoms in a chain or ring are bound to a central atom, numerals indicating these ligand atoms are also inserted preceding eta to the power of n. So as you can see in the next page, so there are two pentarings. So where there is attached to these are attached to the carbonyl and molybdenum. So where here you can call this compound as bis tricarbonyl eta to the power 5 cyclopentadienyl dimolybdenum. So this is how we have to name any compound. So next also you can see where, so it is a tricarbonyl group. So where it is written as tricarbonyl 1 3 eta to the power of 3 2 butynyl cobalt. So this is how you have to include these additional rules in naming of any of the organometallic compounds. So now coming to the EN rule. So there is two rules with respect to this. Actually there is 18 electron rule. Another one is 16 electron rule is also possible in some of the complexes like square planar complex. First we shall see what is an 18 electron rule. A complex in which the central metal atom appears to have acquired the configuration of an inert gas by transference or by sharing of electrons tends to be more stable. This generalization is known as inert gas rule or electron rule. That is, in an organometallic compound where central atom have 18 electrons, that is total number of electrons can be come from the metal, ligands and surrounding elements. So now how you will count these 18 electrons, we shall see. The total number of electrons which the metal atom appears to around itself in the complex is called effective atomic number of the metal in that complex. So in coordination compounds we use it to deal with the EN rule also, where there in coordination compounds the inert gas configuration was about 36. Now here we are discussing about 18 electron rule. The 18 electron rule implies that in a metal complex 18 electrons are made available to the metal through bonding, and then metal assumes electron structure of the next noble gas. So now where these the 18 electrons comes from, the 18 electrons are accommodated in the 5 n-1 d orbitals. That is, each d orbital can accommodate a maximum of 2 electrons. If there are 5 d orbitals, then 10 electrons. 3 np orbitals, each orbital can accommodate 2, so therefore it becomes 6 electrons, and 1 s orbital, that is 2 electrons. So 10 from d, 6 from p and 2 from s, so totally it becomes 18 electrons. These electrons comprise the electrons of the metal along together with the electrons contributed by the ligands also. So 18 electrons. So now I think you have understood the 18 electrons comes from the uh, d orbital, that is metal, as well as ligands. The attainment of 18 electron configuration leads to the stability of complex. So just like in case of coordination compounds, how 36 will give an inert gas configuration, here in case of organometallic the 18 electron rule is applied. So what are some of the, how do you count the effective number of electrons in these organometallic compounds? The effective number of electrons in valency shell, that is in n-1d, ns and np orbitals of metal in a given complex, are counted by following procedure. First point, count the number of electrons in the valency shell of the free metal atom, that is valency shell includes n-d orbitals as well. Add or subtract electrons according to as charge on the metal in the complex is positive or negative. If it is an element, then it is 0. If it is positive, then so depending on that you have to add or subtract. If there is charge on the metal, then you have to add or subtract depending upon whether charge is positive or negative. Check the number of electrons which organic ligands formally contribute to the valency shell of an atom in accordance with the classification of, that is, number of electrons contributed by ligand for the metal carbon bond. So here in case of the number of electrons donated by organic ligands here, so when we see say metal, so metal is generally not only metal, the ligand can be also an organic ligand. So this one you have to observe very carefully. So ligands, there are monodentate, didentate, as we have seen in case of coordination compounds, up to heptadentate ligands. So carbonyl in this case for organometallic compounds is treated as special ligand because each terminal carbonyl contributes 2 electrons and each bridging carbonyl contributes only 1 electron to the valency shell of the metal atom. So now the third point is check the number of electrons donated by the valency shell of the atom by conventional ligands present in the complex, that is other than organic ligands. Now check the number of electrons formally contributed to valence shell by metal-metal bonds. The bonds also here is considered as a ligand, or to the total number of effective atomic number, bonds are also here considered. Each metal-metal bond contributes 1 electron to the valency shell of the metal in the complex. So right now we have seen the 4 rules for counting number of electrons, that is one from the metal, so another from the organic ligands, another from the other ligands other than organic ligands, and another by metal-metal bonds. Each metal-metal bond gives a value of 1 electron. Summation of number of electrons, that is by adding up all these steps, checked in steps 1, 2, 3 and 4, give the effective number of electrons in valence shell of atom, and that's complex. If total number of electrons from all these points comes to be 18, then that metal complex holds good for like 18 electron rule, that is that complex is stable. Thank you. So next remaining we will continue in the next video.